Hey, thank you.
Oh, that's okay.
All right, so last speaker of the morning. Sorry. Jason, just go ahead.
All right, so hello everyone. My name is Guochao Jason Sun. I'm a postdoc based at Northwestern University. So first of all, I would like to thank the organizers of this very nice workshop for giving me this opportunity to speak here. So today I'm going to talk about some recent work we did on understanding the implications of bursty star formation for high redshift galaxy observations with JWST, which is based on an analysis of a suite of high redshift simulations from the FIRE project. All right, so from the many very interesting talks and discussions we've heard so far about like high redshift galaxy observations with JWST, I think the puzzle about having a higher than expected abundance of UV bright galaxies at cosmic dawn should be pretty clear. So without like trying to restate the problem again, I'll just quickly point out that this like quote unquote tension between cosmological galaxy formation models and also new observations from JWST is what motivated our study. And as we have also heard about that, as many like other interesting but like unexpected discoveries in astronomy nowadays, this has turned into exciting game for astrophysicists who very quickly come up with a number of promising ways to crank up the abundance of UV bright galaxies at these early epochs. So including higher enhanced star formation efficiency due to, for example, inefficient feedback or some AGN contribution or dust or like population 3 stars or top-heavy IMF, and also the like holy grail of modern astrophysics, which is to break the standard cosmology. Okay, so well, all of the like the possible like mechanism I just mentioned could work, at least in principle. For today's talk, I'm going to focus on another promising possibility, and according to our vote yesterday, this seems to be our local favorite solution, which is bursty star formation. So as you can see from the quick illustration on the left, bursty star formation history can naturally give rise to some like fluctuations in the UV luminosity, which in turn can elevate the bright end of the UV luminosity function by upscattering the fainter but more abundant galaxies from the sort of like fainter end of the luminosity distribution. So, and another thing I want to mention is that actually there has been like observational evidence for increased level of star formation burstiness from the JWST observation we have so far. So for example, in this figure from Lucer et al., you can see that by using the ratio between the nebular and continuum emission as like a tracer or a metric for the level of burstiness, there has been it has been shown that low mass / high Z galaxies tend to be to have like a more bursty star formation history, and this might have some connection with the need of like a deep enough gravitational potential in order to resist feedback regulations. So combining these like theoretical speculations and also the observational evidence, it seems like bursty star formation could play an important role in shaping the luminosity distribution or the abundance of UV bright galaxies at these early epochs. Okay, so in order to understand the exact implications of bursty star formation for the abundance of UV bright galaxies at cosmic dawn, we turned to a suite of high-redshift FIRE2 simulations, which were developed and introduced by Xiangcheng Mai back in 2018, well before the launch of JWST. And these high-resolution simulations are able to explicitly resolve the star formation and also multi-channel stellar feedback in the multi-phase interstellar medium. And as a natural prediction of these simulations, the high-redshift star formation turned out to be highly clustered and highly time variable. And another thing I want to stress about these suite of simulations is that these predictions about the clustering of star formation and also the burstiness of star formation are based on simulations with standard cosmology and normal star formation efficiency. Okay, so here is a master plot showing the upshot of our UV luminosity function analysis. It's a little bit busy, so I want to try to proceed slowly. So here along the top row, we show the relation between the UV magnitude and halo mass extracted from individual stimulated galaxies from the suite of data we have. And so in order to extract the UV luminosity function from our suite of zoom-in simulations, we effectively convolve this UV magnitude halo mass relation, the full distribution of the UV magnitude and halo mass relation with the halo mass function by assigning weights according to what the halo mass function tells us. So here, and then in the bottom row, we show the corresponding UV luminosity predictions at these different redshift that are derived from basically from the upper panel. So in order to gauge the exact kind of impact of bursty star formation on galaxy abundance, we further define two contrasting scenarios. So in the with varying level of burstiness, and this is what we use to evaluate the UV magnitude from our simulation. So basically, in the first scenario, which we call bursty, the UV magnitude is derived or evaluated directly from the SED of individual star particles without any modification. So it is derived as is from what our simulation suggests. Whereas in the second contrasting scenario, which we call smooth, the UV magnitude is derived from star particles with after a redistribution of their stellar ages, or if you want, star formation times, to even out the star formation rate fluctuations over some given time scale. So there are some smoothing kernel associated with this smooth scenario. So basically, if you compare from the comparison between our simulation predictions and observations, and also the comparison between the bursty case versus the smooth case, we have two major findings. So first of all, from our simulations without any fine-tuning about the star formation efficiency, cosmology, or the IMF, can actually pretty well reproduce the observations, at least within this redshift range, from redshift 8 to 12, which is motivated by the availability of SPEC-Z measurement and also where we expect attention could exist. And so this is the first implication. And the second important finding we have is that the bursty star formation appears to have an important role in shaping the UV luminosity function at the bright end at these redshifts. So which can, for example, at redshift 12, you can see there can be order of magnitude difference that is caused by whether, depending on whether you look at the bursty case or the smooth case. So the importance of burstiness can be basically seen from the contrast here. All right, so we can also put our simulation predictions into the context of the predictions from some other cosmological simulations, such as Millennium TNG flares or CODA 2. And so from the comparison here, can see that like overall, our FIRE2 simulations tends to predict like higher Brighton abundance and also like a more milder evolution across this redshift range, and also the large dynamic range enabled by our high-resolution simulation allow us to probe toward like a much fainter regime of the UV luminosity function. And to better describe this result, we also provide and show that the UV luminosity function across this redshift range can be well fit by universal double power law, where each of the parameters is allowed to evolve as a single power law in redshift. And just as a quick spoiler, so if you're interested in the faint end or low mass end of the galaxy distribution at these early epochs, and also their connection to the local fossil record, please check out Pratik's talk on Thursday, which is also making use of FIRE simulations. Okay, so then we can also, with the UV luminosity functions in hand, we can do like a very straightforward integration down to some limiting magnitude to see how our predictions of the UV luminosity density compared with observations and also some semi-empirical models from the literature. So basically from the comparison with observations and models here, we see that we predict the overall, the agreement with observation is pretty good over this redshift range. And also we compare with the other like semi-empirical models, where we predict somewhat milder evolution of the UV luminosity density. And then in terms of the contrast between the bursty and smooth cases, there's a clear like 0.5x offset in terms of the normalization. But we don't see like a very clear difference in terms of the steepness of redshift evolution. So although this offset here is small, partly because the faint end contribution comes into play, this is like still matters if we want to do a careful comparison with the observations. All right, so now that we have discussed about the implications of bursty star formation for the abundance of galaxies at cosmic dawn, let's just like shift gear a little bit to talk about some other implications of burstiness for galaxy observations in general. So here in this other recent work, we look into the implications of bursty star formation for the observability of galaxies. So what do we find? So I think the upshot is that for galaxies near the detection limit of a given survey, as the star formation rate of the galaxy fluctuate, it can very easily oscillate in and out of the observable regime. And so as such an effect is shown in terms of the mock images here on the left, where we show the mock image from our simulations for example galaxy Z5 M11b at redshift 8, 7, and 6, respectively. And whereas on the right, we show the star formation history and the corresponding redshift evolution of the period magnitude in several JWST filters corresponding to this example galaxy Z5 M11b and also another more massive galaxy Z5 M12b. So from the connection between left and right, you can see that the flickering of this galaxy is caused by a major starburst occurred at redshift 7, which caused the galaxy to oscillate into the observable regime, going from redshift 8 to 7, and then migrate out of the observable regime again as the SFR drops from redshift 7 to 6. So by tracing the observability of individual galaxies, we can also use our galaxy sample to characterize what is the observable fraction as a function of galaxy mass, redshift, and also the survey depth. So here in this plot, I'm basically showing 3 example surveys, Sears, J's medium, and J's deep. And not surprisingly, we can, if we look at how the observable fraction behaves, we can see it increases with increasing mass and survey depth, and decreases with increasing redshift. And if we think about like the modulation of galaxy observability by bursty star formation, then we can look at some characteristic observable fraction of 50% or so as like a very rough measurement of like galaxies sitting at the boundary of like a detection limit. And this another implication of this is that if we want to think about a mass complete sample, then it is really important to understand factors that can complicate the observability of galaxies, such as the bursty star formation that is discussed here. All right, so finally, we also want to look into whether or not the modulation of galaxy observability can give rise to any appreciable selection effect when it comes to like the inference of galaxy properties. So here I'm plotting basically the detectable sample versus non-detectable sample for a galaxy within a pretty narrow stellar mass bin. And here I plot the distribution of 3 different galaxy properties: the cold-dense gas fraction as the field of star formation, the specific star formation rate, and also the gas phase metallicity. So from these distribution here, we can see that for cold-dense gas fraction and also the specific star formation rate, there's a clear offset for the detectable sample being like biased towards like higher values, which is like this order of unity difference between the detectable and the non-detectable sample. So because we know that like a higher cold-dense gas fraction and also a higher specific star formation rate are characteristic of like galaxies in the starburst phase, it is likely that the offset here could be like a consequence of some selection effect due to the modulation of galaxy burstiness, the modulation of galaxy observability by burstiness. So this kind of like selection effect in terms of for galaxies near the detection limit should be taken care of if we want to like properly assess the galaxy properties that are sensitive to the SFR variations. Okay, with that, just in the interest of like everyone's emptiness in their stomach, I'll just stop here and take your questions. Thank you.
Thank you, Guochao. Any questions? Quick question.
Sorry, I missed that. What caused the burstiness?
So I think the major driver of the burstiness is at least in the fire simulations, the multiple channels of stellar feedback, so supernova, radiation pressure, etc. Yeah.
So we've heard about these feedback-free galaxies and the dust clearing and all these things. It seems like fire sort of does it kind of already include these things, because you are tracking the stellar evolution and you have very high resolution and all these things. So do you implicitly include these effects?
To some extent, but of course we made some like specific assumptions about like the instantaneous star formation rate, star formation efficiency, and also like what like channels of stellar feedbacks is included. So it will be interesting to make some like more direct connection between these like simulation result and like specific like analytic scenarios. But yeah, depending on like which angle you want to like make the connection, happy to discuss more. Yeah.
All right, one last question from Abhishai.
Well, I just want to complete the answer to Romil. This is Fire 2 simulations. In Fire 2, there is threshold for star formation at 1,000 atoms per cc. In some ways, this mimics the conditions for feedback-free starburst.
But I want to make a like quick clarification here. So about like Avishai's point. So yes, in these Fire 2 simulations, we do impose like a density criteria for like above which the star formation can happen at a fairly high star formation efficiency. But like It's also important to know that star formation only occur in a very dense region, very dense gas within like fire simulation. So if you consider some like time integrated and global average star formation efficiency, our galaxies tend to be follow some like more or less normal star formation efficiency, and this can be seen in terms of these like stellar mass halo mass relation, and you can see that we still predict fairly clearly suppressed star formation efficiency when it comes to the low mass galaxies.
All right, so let's thank Guochao again and all the speakers this morning, and let's get for lunch.